So remember, we were showing, this is number 6 in the properties of convolution, right? That if you take the convolution and then you take the Fourier series, that the Fourier series of the Fourier coefficients of the convolution are going to be the product of the Fourier series of the things, right? Of the individual guys. Do you guys want me to run over that again? Because I kind of ran over it quickly at the end. If not, if you feel good.
I think that would be helpful.
Oh, it'd be helpful. Okay. Okay. So, so the proof went in 2 steps. So step 1 was show this for continuous functions, right? Okay, and that was using that using Fubini's theorem. And I hope you all saw the message about why Fubini's theorem doesn't work for Riemann integrable functions. So there's, Jaden had said, well, can't you just use this proof for integrable functions? And it turns out that Fubini's theorem doesn't necessarily hold for integrable functions, but it does for continuous functions, so you can use it. Okay. Okay, so step 1 was show for continuous functions. I'm not going to redo that. Step 2 was to now do it for integrable functions. So f and g, so these guys are integrable, Riemann integrable functions. So now we assume that these guys are integrable, and we play the trick of letting that we have continuous functions that are converged to the integrable functions. So recall we have this lemma. So by the lemma, there exist sequences fk such that fk and gk of continuous functions such that fk converges to f and gk to g in L1, right? In other words, that the limit of fk minus f goes to 0, and gk minus g goes to 0. Right, and these guys were bounded with the same bounds as the original functions. Okay, so I'm just sketching over what we did at the end of last time. Right, and so what's the point? For these guys are continuous, so we can apply. We already showed this statement for continuous functions, right? So by part 1, we know that fk convolved with gk converges to fk convolved with gk is the convolution, the Fourier series of the convolution equals the product of the Fourier coefficients of the convolution is the same as the product of the Fourier coefficients of the individual guys, right? So, right, because they're continuous, right? Okay, and also recall we showed that fk convolved with gk. We showed this earlier that fk convolved with gk converges uniformly to f convolved with g. Okay, so we did that in the earlier in the proof of part 5. Okay, so that these things. So this is uniform convergence here. Okay. So that uniform convergence implies that the Fourier that if we take the Fourier coefficients on the left side, then that actually the limit of that actually turns out to be the Fourier coefficients of the right side. Okay, because when you take, what happens when you take the Fourier coefficients, you're taking the integral of this thing against the character, right? You're taking the integral of this thing against the character, right? And we want to talk about the limit of the integral, the limit of that integral, right? But uniform convergence allows us to say that the limit of the integral is going to be the integral of the limit, right? It's going to be the integral of the limit, and so we get the Fourier coefficients of the right-hand side. Okay, is that okay? Okay, so here we use the uniform convergence. So uniform convergence allows us to switch integral and limit. Because when we're doing this, what we're doing is we're taking an integral of the sequence. So we can switch integral. We're taking limit of the integral of the sequence. We can take the integral of the limit of the sequence. That gives us this. Okay. I'm cheating you slightly, but not significantly. So check. Do it yourself. There's just this small detail that needs to be checked. It's very tiny. Okay. So what do we have, right? So by part one, we have that that this thing is this thing, right? By part and right now we've just seen that this thing converges to this thing. Okay. So putting those together, we have together. We have that this converges to this. Right? As k with k. Okay, so the only thing we need to do is show that each of these guys goes to, that this, we want to show that this goes to f hat n and this goes to g hat n. Okay, if we can show that, then we're done. Okay. But that turns out to be very simple. Okay. You say, okay, well, consider so claim f hat, fk hat, and converges to f hat n. So what's fk hat n? Can you just tell me? The left-hand side is 1 over 2 pi integral pi x of k x e to the minus I and x dx. Right? And we want to show that turns into the right-hand side, right? So let's look at the difference. We subtract off the right-hand side. Fx e to the negative I and x dx, right? Right. So the difference. The difference is this, right? And then what are we going to do? We're going to put them together, and then we'll use the triangle inequality, as always. We use the triangle inequality, we get fk minus f e to the negative I and x's absolute value, which is 1, and get dx. Right? And that is the L1 norm of the difference, right? That's the L1 norm of the difference, which we know goes to 0. And so we know that this goes to that. Okay, and similar, identically for G. Okay. Yeah. This is a useful fact, right? We should probably make this a lemma, right? That look, if fk converges to f in L1 norm, then the Fourier transforms of fk turn into the Fourier transforms of f. That may come in. That will come in handy. It already has come in handy. Yes, Kai.
For when you said like switch integral with limit, is that, I might have missed this. Are we using dominated convergence or something weaker? Or?
We're using the fact that we had uniform convergence.
Oh, yes, with you. Yeah.
Okay. Okay, everybody all right? So I hope you guys see the overall strategy, right? You know, you're trying to prove something about integrable functions, you prove it for continuous functions first, right? And then you use the fact that integrable functions can be approximated by continuous functions. And there's a nice, you know, and that these, you know, that the Fourier coefficients of the approximating guys turn into the Fourier coefficients of the original guys. Okay, let's go on. Okay, so let's go. Yeah, so now we're going to go to the section called good kernels. We're going to talk about good kernels. Yeah, another name for this is called approximations of the identity. That's actually a more common way of saying this. Okay, so right, so we're looking at our space of functions, and we're looking at functions on the circle, and we have this sort of way of taking multiplication, right? We have a kind of multiplication on these functions. So normally one restricts to L1 functions on the circle. So you've got L1 functions with a convolution, with this multiplication operator. Okay. So you might ask, is there an identity, a multiplicative identity? Right? Is there a multiplicative identity? Some function that you would convolve against, right? You have, right? Some function that you would convolve against, and then just get back f of x, right? So in the ideal world, G would be the Dirac be the so-called Dirac delta function. Which it would be 0 everywhere. So if G were this Dirac delta function, you think of this thing as sort of being a mass of 1 at 0, a mass of 1 at 0, and then 0 everywhere else. Okay, so a mass at 0 and then 0 everywhere else. And then you would integrate against it. You'd say, okay, this is going to be 0 except when y equals x. Right? Except when y equals x. So only when y equals x do you get something, and it will just return the value at that point. That's what the Dirac delta function would do. So the Dirac delta function is sort of like the what you would want as your identity. It is the identity element, but it's not a function. Okay, it's not a function. It's what's called a distribution. Okay, so there is no identity element. This is a ring. It's a, I know you've seen this term. It's a ring, like a ring without an identity. Yeah. That actually is enough. I've seen that in books, in at least one book. Okay, so instead, you know, we don't have an identity element, but we can create things that approach an identity element. Okay, so that in the limit act like an identity element, and that's what these things called the approximations of the identity, or good kernels. Okay, so here's the definition. So you've got a bunch of functions. You've got a bunch of kernels so these are a sequence of functions on the circle. Okay, so which I'll abbreviate like this in the future. Okay, so T stands for torus. The one torus is the circle. Okay. So you have a bunch of functions on the circle, and so if they satisfy 3 conditions, then they will act as an approximation of the identity. Okay. So the first condition is 1, that the integral has to be 1. Okay. And I call this the sliding in condition. Nobody calls it. That's not an official term. Just the sliding in condition. Okay, 2, you want the integral of the absolute value to be finite. Okay, so this is really is an L1 condition, right? That your function is in L1. It's absolutely integrable. Okay, and then 3 is that for any delta greater than 0, if you consider the integral over the place where x is bigger than, absolute value of x is bigger than delta, you consider the integral of your function, the absolute value of your function over the place bigger than delta, so away from 0. So you're saying that if you look at your function away from 0, then the limit of that as n goes to infinity is 0. Okay. In other words, right, these guys, the mass of these guys, as time goes on, the mass of these guys bunches in towards the origin, right? So like you have pictures of good kernels often look something like this. Maybe the first one looks like that, the second one looks like this, the third one looks like this, right? As time goes on, the mass away from 0 tends towards 0. Okay, so this is sort of like a concentration of mass condition. Okay. Okay, so so if all these things happen, then we call this set of functions, the sequence of functions, an approximation of identity. An approximation of identity, or a family of good kernels. Everybody all right? So 3 conditions, right? The sliding condition, the L1 condition, and the concentration condition. Okay, you got them? Then you're a family of good kernels. Okay. So here's the theorem that justifies calling them an approximation of the identity. So let f be an integrable function on the circle. Let k sub n be approximation of identity. Then, if f is continuous at a point, then the limit of f convolved with k sub n at that point is f at that point. So you recover the value as n goes to infinity, convolving against this approximation of the identity actually gives you back your function at that point. Okay. And of course, if f is continuous everywhere, then this happens, then you recover your function everywhere. But better than that, in fact, f convolved with k sub n converges uniformly to f. Okay. Fine.
We proved that convolution is always continuous, right? So the, oh, no, yeah.
Yes.
Yes.
No, it works out, yes.
My questions.
Nope, you're good. Okay, so let's do the first part, right? So, suppose f is continuous at some point x naught. Okay, and we want to show that this thing converges to that thing. So we consider the difference as usual, right? F convolved with k sub n x naught minus f of x naught. Right. This turns out to be pretty straightforward calculation. You get 1 over 2 pi negative pi f of y k sub n. Let me do it in the opposite direction. Sorry. K sub n of y f of x naught minus y dy minus f of x naught. Okay, so it's just definition. Right. And then we use the sliding in condition. So we say, well, look, this f of x naught, I'm going to rewrite that as f of x naught times 1. Right, times 1. Right, so I've got this nice looking 1 here. Right, and that allows me to combine these two things together in one integral. Right, so I can slide this thing into here and then put them together. Right, so I get 1 over 2 pi, negative pi to pi, k sub n, f of x naught minus y minus f of x naught dy. Okay. Okay, so think, what's our goal? We want to make this as small as, given any, so we want to show that, given any epsilon, we can make this thing smaller than epsilon, right? For n bigger than some n bigger than something. So fix an epsilon. Okay. Fix an epsilon. We want to make this thing smaller than epsilon. Okay. So, as usual, we use the triangle inequality. Right. That's going to be smaller than this. Smaller than this. Right. Okay, so we want to make this thing small, and we've got various facts about the good kernels, right? One is that that you can concentrate things in as time goes on. You can concentrate things in towards the middle. Another is that its L1 norm is finite, right? Okay. We also have that f is continuous at x naught, right? F being continuous at x naught means that if y is tiny, then this difference is tiny, right? Right? Because then this thing is close to x naught, right? So choose delta such that if y is such that if y is smaller than delta, then the difference between f of x naught minus y and f of x naught is smaller than, say, epsilon. Okay, and we'll fix that up. We'll fix that epsilon up in a second. Okay, so just by continuity, right? As long as y is small, then this thing can be made small. Right? That's just continuity. Okay, so okay. Okay.
Yeah.
Is it good? Yeah, it's good. Do you have a question?
No, I'm
No,
not.
Justin had a revelation.
Revelation. Okay, even better.
Yeah.
Better than questions. Revelations. That's great. Great. Okay, so so now what we're going to do is break this integral up into two parts. We'll break it up into y being small and y being away from the origin, right? Y being close to the origin, right? Y being close to the origin, y being away from the origin. When we're away from the origin, we can make it small by condition 3. When we're close to the origin, we just use this condition here. Okay. So we break this thing up into two parts, right? That thing is going to be the integral between negative delta and delta. Right, plus the integral for y bigger than delta. Oops. Okay. And you guys can probably do it yourself, right? So what happens, what kind of bounds do we get for this first thing? Right? Take 1 minute and write something down. Okay, finish the proof. Okay, take 1 minute and finish the proof.
How hard is it raining, or is that just water coming up the top?
It's not raining.
And, yeah, it's just water. It's not raining at all.
Why does this building do that a lot?
Yeah. You need fountains.
Oh, wow. That's really off. Okay, yeah. I'm with you.
the bound to be a good kernel, like on the integral? Like there's, it has to be L1. Is that uniform across all the integral?
Sorry, say that again. Is the bound be
A good kernel uniform across all the n? Is it the same bound for all the n?
I don't understand which bound.
I don't know.
Is the condition to be a good kernel, like the bound on the integral that says the L1 condition, is that m uniform across all
Yes,
n?
yes,
Oh,
Okay.
I understand what you mean. Yeah.
yes. The bound, all of those guys are smaller than m. All of those L1 norms are smaller than that.
I think it has to be, because we need the L1 norm to go to 1 in the limit, is basically what we're saying without saying.
Yeah.
And so, yeah, and so then it can't not have an upper bound because it's getting smaller.
Mm.
That's what I think, right?
Hmm.
Yeah.
That
Let me
makes
show
sense,
you.
but you're using language that we don't.
Okay.
Yes,
Yeah.
I
You
understand.
guys are talking, let me, but, no, I'll just, no, you're good. I wanted you to talk. So we want to get the bounds here, right? This thing here, right, is smaller than epsilon, right? So this thing is smaller than epsilon, right? And this thing is smaller than the L1 norm, right? Because we're just taking part of the integral, right? We're taking, if we integrate over the whole thing, it just gets bigger, and that would give us the L1 norm, right? In any case, if we pull out, this thing is smaller than epsilon, we're left with epsilon over 2 pi times the integral from negative delta to delta of the absolute value of the kernel, right? But that thing is smaller than m, right? That's smaller than m, right? So we get that this thing is smaller than em over 2 pi, right? Right, so maybe I want to divide this by m and multiply it by pi. Right, so I get e pi over m, and then I get epsilon over 2. Okay. So this is smaller than epsilon over 2. Okay. So this thing's smaller than epsilon pi over m, and we end up with epsilon over 2 for the first term, right? And then for the second term, same sort of thing, right? We know that that this thing, this thing is an integral function, and so this is controlled by some bound, right? It's controlled by twice the bound, right? Where f being integrable is a bounded function, right? So this thing here is controlled very crudely by twice that bound, right? And so we end up with, twice that bound over 2 pi, the integral away from the origin of this thing, right? But by the concentration condition, we know that as n goes to infinity, this thing goes to 0, right? So we can choose an n beyond which this thing is smaller than, epsilon times pi over b, right? So there exists an n such that if n is bigger than n, then this thing is smaller than epsilon pi over b, right? And that would make the second term smaller than epsilon over 2, and so we get smaller than epsilon. Plus this thing, which we can smaller than, can make smaller than epsilon over 2 by choosing the proper n. Okay. Okay, so now notice that, so that proves it, right? If we have continuity, then the convolution with the good kernels converges to the value of the function at the point, right? That's what we've just shown. Okay. So we've shown part one of the theorem. Now for part two, so if f is continuous, if f is continuous everywhere, right, then f is uniformly continuous, right? F is uniformly continuous, and in that case, the delta that we choose doesn't depend on x naught. Right, so delta is independent of x naught. Right. In the first case, that delta depended on our point, right? But uniform continuity means that that delta is going to be usable everywhere, right? Okay. So so what does that give us? That gives us that this n doesn't depend on x naught anymore. If you think about it, the main problem with the obstruction to getting uniform convergence, right? We want uniform convergence, right? We want this n to be independent of x naught, right? Where does this n depend on x naught? It depends on x naught because it depends on the delta, right? When you change the x naught, you change the delta. But by uniform continuity, right, that delta is independent of x naught, and so now we have uniform convergence. Okay, so just you notice that if f is continuous there, then delta is independent of x naught, and so that n depends only now on epsilon, not x naught. Right. You know, here it depended on delta, which depended on x naught and epsilon. So this thing here we had n dependent on delta, which was dependent in turn on x naught and epsilon. Right. But now with uniform continuous, that x naught gets eliminated, and so we're just dependent on epsilon. Right. So we have uniform convergence. Is that clear? Do you guys everybody okay?
Yes.
Right? Like uniform convergence means that, you know, given an epsilon, there exists an n such that, you know, uniformly across your domain, you're within epsilon of your target, right? And that's what we get here.
But we're saying, and we have uniform continuity, so we're saying the delta doesn't depend on our choice of point, and the n only depends on our choice of delta.
Yes.
Right. Okay.
Yes. Yes. Okay, any questions? Any questions? Okay, so this is a pretty typical kind of this sort of argument happens all the time in Fourier analysis or in harmonic analysis. Yeah. Okay, let's go on. So now we're going to see application of this theorem, right? So now what do we have? We have that, you know, if your kernel is an approximation of the identity, if your family is an approximation of the identity, then you can recover your function pointwise, right? You can recover your function pointwise. Right, so Kn good means that this thing converges pointwise, so if your function is continuous, then this thing converges, well, converges uniformly to f, right? And it converges pointwise at any point of continuity if your function isn't continuous everywhere. So that's what we're just showing. What we've just shown, and now we're basically going to do some sort of like application to Fourier series. Okay, so remember the big question for Fourier series is, you're wondering if f convolved with the Dirichlet kernel. Remember, the partial sum guys are f convolved with the Dirichlet kernels, right? And you're wondering, you're hoping that that thing gives you back your function. Okay. It turns out that that's actually not true. That doesn't necessarily happen. Why? Because the Dirichlet kernel is not a good kernel. Okay. So that's sad, but.
Because it's not L1? Yeah.
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 Yeah. So remember that if the function, right, so if f is continuous, right, then the Fourier coefficients, right, so here's the point, right, sorry, I got kind of thrown off. If the function is continuous, then the Fourier coefficients are unique, right?
Mm-hmm.
If the function is continuous, then the Fourier coefficients are unique, right? But the Fourier series may not converge pointwise to your function, to your original function. Right? The Fourier series might not converge pointwise to your function. Remember what kind of result we have. We have that if the Fourier coefficients are absolutely summable, right? Then your Fourier series does recover your function, right? Then, right? If the Fourier coefficients are absolutely summable, then the Fourier series does actually recover your function, but if not, then not necessarily true. Your Fourier series might not give you back your function back. Okay. Right? That's what we know about like recovering our original function at this point. Okay, but I don't know if this is kind of plausible, but you think, well, look, the uniqueness of the Fourier coefficients ought to mean that that there's enough information, even if this Fourier series doesn't give you back your function, you still should be able to get back your function somehow, because these Fourier coefficients determine your function uniquely, right? So anyway, it turns out that you can recover your function, but in a different way. So not by using the Fourier series, but by taking certain averages of the Fourier series. Okay, so, right. Okay, so how can we recover the function from the Fourier series? If not in the direct way, right? The Fourier series doesn't do it for us, right? But it turns out we can take averages of the Fourier series, and that will give us back our function. Okay, and the reason will be that averaging the Fourier series will be equivalent to creating good kernels. Okay, so that's the idea. So there's two methods. One is called Cesaro summability, and the other is called Abel means. Okay, so Cesaro means and then Abel means. Okay, so Okay, so I'm just going to start the idea. Given a series, summation C sub k, let S sub n be the partial sum series. Summation C sub k from k equals 1 to n. So let this be the partial sum series. Okay. Then we define the they call it they give it two different terms. The nth Cesaro mean we define the nth Cesaro mean denoted sigma sub capital N as the average of the first n partial sums. Okay. So you take the partial sums, and you take the average of the partial sums. Okay, average of the first n partial sums, and that thing is called the Cesaro mean. Cesaro mean of the partial sums. Okay, it's really, I mean, you could just leave this word Cesaro out, right? It's the mean of the partial sums. Anyway, it's called the Cesaro mean of the partial sums. Okay, alternate terminology. It's called the nth Cesaro sum of the series, of the original series, C sub k. So anyway, I don't like this terminology, but anyway, I'm just going to call it the nth Cesaro mean. Okay, so when I said the nth Cesaro mean of this series, I mean the mean of the partial sum of this series. Okay, let me just do. How many of you have seen this before? How many have seen Cesaro means before? Actually, you've probably all seen it. It's a common exercise in a real analysis course, in a 131 course, to show that, so this is a standard homework problem in 131, to show that if the partial sums converge to S, in other words, if the original series actually converges, then that forces the Cesaro means to converge to the same limit. Okay. So convergence of the series is a stronger condition than Cesaro convergence. So Cesaro mean convergence. Okay. So yeah. Okay. So let me just give a simple example. It won't take that long. So if we have, for example, -1 to the n from 1 to infinity. In other words, 1, 0, 1, 0, 1, 0, 1, 0. Right? We're adding. Right? We're adding ones and negative ones, and we get 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay. So sorry. So then the partial sums, are partial sums are going to be 1, 0, 1, 0, 1, 0, etc. Okay. Well, in that case, the Cesaro means are going to be the averages of those, right? So we take, the average of the first term, average of the first term, average of the first two terms, average of the first three terms, average of the first four terms, average of the first 5 terms, and so on and so forth. Right? Here we get our partial sum series, and we start averaging, like over the first term, second term, first 2 terms, first 3 terms, first 4 terms, etc. Right? And you see that even though the partial sum series doesn't converge, right? It oscillates between 1 and 0. The Cesaro mean actually converges to 1/2. Okay, which is kind of a reasonable thing to think about. Yeah, in fact, when Leibniz was first talking about infinite series, he thought that this thing should converge to 1/2. I think in his system, he had some way that he had some definition in which this actually converged to 1/2. Okay. I don't know if he was using Cesaro means, but anyway. Okay, so I hope you guys, so this is an example showing, look, partial sums don't actually converge, but the Cesaro means do converge to something. Okay, so next time we'll apply this to Fourier series and see that we can actually recover the function using the Cesaro means of the Fourier series. Okay. See you guys next time.